Okay, welcome back, class. Today we're going to continue our discussion on electrons and electron behaviors by discussing light waves. Today our objective is that you would be able to understand and explain the photoelectric effect along with how it creates ions. Okay, so let's dive into this. Whether you are looking at a house, a car, or even a chair, we can see the components that make those structures up. There are always smaller components that make up larger structures. For example, we can see the bricks that make up a house. If you open the hood of your car, you can see the different gears and pistons that make up in your car, make it run. And you can even look at the chair you're sitting in, and I bet that you can see the screws or bolts holding it together. Where I'm getting at with all this is that we can see the components that make up the world around us. But how do we see the different components of an atom, which is supposedly the building blocks of everything we see? Let's bring up another illustration to further this dilemma. If you hold your hands close to a light bulb or fire embers for a while without touching the bulb or the embers themselves, then your hands will eventually start getting warm. In other words, the energy emitted from these sources of light was enough to transfer to your hands and warm them up. This means that light, whether it comes in the form of fire or white light, contains energy. Up till now, we have assumed that we can directly observe subatomic particles. The reality of this situation is that we cannot directly observe all subatomic particles. Electrons are significantly smaller than protons and neutrons, and for us to visually see them, we must have light. As we said earlier, light contains energy. And because of how small electrons are, that energy alters the pathway of the electron. In other words, we cannot see how an electron naturally behaves because once we visually see them, the light it took to view them alters the location and pathway of the electron. Because of this, we have only been able to theorize the behavior of electrons through the quantum mechanical model or through electron orbitals and configuration. In order to start to understand the nuances of this model and why we theorize that electrons behave the way we think they do, we must first understand the nature of light, both as a wave and as a particle. To understand the duality of the nature of light, we first need to explore light as a wave. Light is a form of electromagnetic radiation. This means light energy contains both an electrical field, where electrically charged particles experience a force, and a magnetic field where magnetic particles experience a force. These two fields orient themselves perpendicular to each other. We can see an example of these types of forces when we bring each of these types of fields within contact to its partnering type of field. If we bring two oppositely charged electric fields close to each other, then they will be attracted to one another, thus altering the field's pathway. Same concept works with our magnetic field. These waves of electromagnetic radiation move extremely fast, and even faster than the speed of sound. This is why we can visually see fireworks before we hear that explosion. Each wave consists of the following: wavelength, amplitude, and frequency, which can alter the characteristics of the wave. The amplitude of the wave is the vertical height from the crest or depth of the trough. The amplitude of the wave determines the light intensity or brightness. The wavelength of a wave is the distance between two adjacent crests. The wavelength determines the color emitted from the wave. For example, as I transition my red light wave and decrease the wavelength, I can see that the wave will change to yellow and eventually violet. The wavelength and amplitude are both related to the quantity of energy carried by the waves. A good way to visualize this is that it's still going to require a good amount of energy to swim in the ocean, whether you have large amplitude waves, in other words, large waves, or frequent waves, or a whole bunch of waves, in other words, a short wavelength. Wave frequency is the number of cycles of a wave crest that passes through a given point within a given amount of time. The unit for frequency is hertz, and it can be found by dividing the speed of light by the wavelength. Now that we understand that light's intensity is determined by the amplitude and the color is determined by the wavelength, why do we see the red color when we look at a stop sign? This is simple because we see what light spectrum is reflected off an object. So, for a red stop sign, it might be bombarded with green, blue, white, and even red waves, but the only type of light wave that is reflected off the sign is the red light. So that's why we see a red stop sign. Visible light only makes up a small portion of what we call the electromagnetic spectrum. This spectrum contains all of the wavelengths of all the forms of electromagnetic radiation, from lowest amount of energy produced to highest amount of energy produced. The electromagnetic spectrum consists of the following: radio waves, microwaves, infrared rays, visible light waves, ultraviolet waves, X-rays, and gamma rays. Before we can move into light as a particle, we must briefly talk about what happens when a wave experiences interference or diffraction. Interference is when a wave interacts with another. They can either build on each other in the form of constructive interference or cancel each other out in the form of destructive interference. This is depending on how the waves line up when they come in contact with each other. If the crest of one wave matches up with the crest of another wave, then the waves will build upon each other, while if the crest of the two waves do not match up, they will end up canceling each other out. Diffraction occurs when the wave encounters an obstacle or slit that is comparable in size to the wave. What happens here is when these waves come in contact, they diffract, or they bend around or through the barrier. Now that we have talked about light as a wave, we can talk about it as a particle. The best example of light acting as a particle is the photoelectric effect. The basis of the photoelectric effect is when light shines on a metal, that metal will then emit an electron. The interesting finding about the photoelectric effect was that electrons were only emitted if certain thresholds of frequencies were met. If the light wave frequency did not meet that threshold, there was no electron emitted, no matter how intense the light wave was. Well then, how is this pertinent to light as a particle? Well, Albert Einstein proposed that light energy must come in packets. These packets he called photons. He theorized that in order to dislodge an electron from its position, the energy produced by the force of a single photon must equal at least the binding energy emitted by the electron. So, in other words, this photon must have the energy to break the electrostatic forces holding the electron to the nucleus. Einstein also theorized that any energy left over in the photon after it has met the binding energy threshold was converted into kinetic energy in the electron, causing the electron to move away from the atom. This understanding of the photoelectric effect holds true to today, even with our advances in technology. Now that we have an understanding of light, we can talk about how it applies to electrons and electron configuration. Chemists have developed a technique that utilizes the photoelectric effect to measure electrons' bond strength within an atom called the photoelectron spectroscopy, or PES for short. PES works by creating ions out of a substance using high energy radiation to measure the kinetic energy produced from ejected electrons. With the given energy of a radiation and the kinetic energy of the ejected electron, we can find the binding energy of that ejected electron by simply subtracting the kinetic energy of the electron from the energy of the radiation. In other words, HV minus kinetic energy, where H is Planck's constant and V is the frequency of the wave. A PES then will create a PES spectrum, graphing the photoelectron count versus binding energy. The peaks on this PES spectrum will correspond with the electrons in different subshells of atoms, where the peaks with the lowest binding energy correspond with our valence electrons or outermost electrons, while the highest peaks represent the binding energy of the innermost or core electrons. This then can be used to determine the number of electrons in each orbital and or subshell to validate our electron configuration model. Okay, so I feel that I've bombarded you with a load of information about lights and electrons, so I feel this is going to be a good place for us to stop for now. I hope this video helped you out, and keep up the good work in your class. See you next time.